Lesson 1.3 is about piecewise functions. You're used to functions that might be like x squared, or absolute value of x, or y equals 3x plus 7. Those have been one simple function graphed. We also have talked about restricting the domain recently, but now we're going to combine those two ideas and put multiple pieces of functions together in various domains. For example, if we look at this graph, we can tell there's one chunk of the graph here, and then a separate chunk that's sliding down in the middle, and a third chunk that's going up to the right with a positive slope. Our goal is to identify each of these parts, talk about the domain that they're going over, and give them the equation that goes with them. Let's start with this teal blue function. This is a function that's actually pretty easy to write the equation for because it's very steady, but we're just not used to it. Whenever a line is flat and horizontal, every y value here along the way is 5. So we actually just say this equation is y equals 5. Now this blue section, I guess we'd say the black one that we circled here, we can tell it has a negative slope. And if you've been reviewing anything about making the equations of a line, you know the y-intercept is a key point, which would be 1. And our slope is down 2 to the right 1. Down 2 to the right 1. So this one we would say is y is equal to negative 2x plus 1. Finally, the red graph, it's increasing here. I can tell it is going from this dot here, rising 1, 2, 3, and going over 1. 1, 2, 3 over 1. So when we say rise over run, we'd be thinking 3 over 1 this time, which is just reducing to 3. Therefore, our equation is y equals 3x. The problem is now we don't know what the y-intercept is. You'd say, my graph runs out of space here. I just can't do that. Well, we could go backwards. Let's step down 3 steps. So I'm going to make a couple more marks here. You may have to do this from time to time. Go down 1, 2, 3, back 1. Down 3 more. 1, 2, 3, back 1. So this would be where our graph would have a y-intercept if we extended it all the way. This being at negative 3, we go 4, 5, 6, 7, 8, 9. If we would have gotten there, our y-intercept would have been negative 9. We're going to now take all 3 of those equations and put them into one equation to give us our piecewise. We start piecewise equations by saying maybe p of x equals, and we use our big swiggle brackets to put all the parts in there. So our first equation in blue, we know is y equals 5. We use a comma to separate it and tell us the domain. Now this arrow indicates it's going on forever. So I'm going to say, I could say negative infinity, but I'm actually just going to say any x value that's lower than negative 1. I'm going to draw a line there to show you that that's kind of my bookend. So I'd say where x is less than and equal to negative 1. Now my middle function, we know that's y equals negative 2x plus 1. And it is going from, if I draw my bookend, at negative 1 to positive 2. This is where we're restricting that domain. So I'm going to put negative 1 and my x and my positive 2, point my arrows to the left. And one thing to be careful about is this gator underneath, the equals to bar underneath the gator. You can use that again here if you want to. I'm not going to because it's already accounted for since they meet up right here. But I will put one on this too. Now finally, our third equation that we wrote in red would be y equals 3x minus 9. And that one is going from this bookmark here at 2 all the way up until 5. So from 2 to 5. And at 5, notice the circle was open. And so I'm going to make sure I don't use the bar underneath here. Okay, I don't want to put an equals to because it doesn't actually close at 5. That was an open circle. Now, that was a lot. Let's talk about some steps you can use when you're trying to create equations for piecewise functions. They say first, notice how many pieces there are in the function. Second, determine the domain of each of them. Third, use the graph and its points to determine the slope and y-intercept of the graph. And then finally, create the equation of the line or the function, if you will. So let's try another one. This is in your packet. It's on the try it, number 2. And that goes with example 2. So this will be under example 2 in 1-3's work. All right, so we're going to look at part B here. I'm going to zoom in on a closer screen for us. Notice that we have, let's do our steps. First, we have 3 separate pieces. The next step they tell us is to identify the domain. So I'm going to think about bookends here. Here would be my first start and stop. That's from -3 to -2. So I'm going to go -3 is less than or equal to x is less than -2. Notice how I did not use the equals to on the second one because it's open. The second domain, or the second chunk, goes from -2 to +2. So -2, it does have the equals to because that circle is filled. And then it goes all the way up to 1, but not including 1. Remember, I'm only using the x values. Then finally, my third chunk starts at 1 and goes to 2, a very small window. It does include that 1 value, and it does include that 2 value. Now, the third step says to identify the equations of each of these. I'm going to erase my bookends, and I want to look at this first equation. It appears that it is a decreasing slope. So in pink here, I have this going down 1, right 1, down 1, right 1. If I were to extend that all the way, my slope would be a -1. I've actually kept going so that you could see my y-intercept if I would have made it all the way. It appears that it's 0. So my first equation would be -1x plus 0. And I don't have to write that 0. Now, my second function is that boring flat one. It's actually the easiest one to write, where I would say it's a nice 1 all the time. Y equals 1 all the way across. Finally, my third function, it is sloping up 1, 2, 3, 4 to the right 1. So my slope will be 4 here, but I want to find that y-intercept. I'm going to reverse the process and go down 1, 2, 3, 4, back 1. That would be where my y-intercept would be if I extended it. So my equation, my slope is 4, and my y-intercept would have been at -5. That should give us our piecewise function for this graph. Now, we will bring back some ideas from the first section in 1.1, talking about increasing, decreasing, positive, and negative. So this is that same graph from your try it that we just did on example 2. But now let's talk about, we could even check our answers. It appears as though we've done a marvelous job. Now, we're going to look at what the domain of this function would be. Remember, we had to look for the domain of all the separate pieces of the function, but now we can cover the entire span. We do want to make sure that if you would ever have a gap, say this function here was moved over a little bit, if there's nothing, let's say at -3, you don't want to include that in your domain. That's not the case this time, but just watch out for that. So in this case, our domain is all the x values that are used. We start at -3, and we have one at -3.5, -2. At -2, this first function on the left gave up, but the bottom one took over. So we have a value at -2, -1, 0. At 1, it looks open, but we do have a function piece down below here. So at 1, we have a value all the way up until when x is 2. So our domain would be from -3 is less than or equal to x is less than or equal to 2. In interval notation, we would like it like this with our solid brackets. Our range is how high and how low it would go. So the y values we use, the lowest y value I see here is a -1. The highest y value I see is a +3. So we would say -1 is less than or equal to x is less than or equal to 3. And in interval notation, we would use our brackets. Now notice we have the gators with a support, if you will, or the equals to. That means the inequality is equal to those values because our circles are filled at each of those end values, whether we're talking about the domain or the range. All right, now let's talk about increasing. When was it increasing? This is where the piecewise functions actually come in quite handy. Remember, increasing means it has a positive slope, so it'd be going up to the right. That spot is right here. We're just going to use this third piece's domain in the piecewise function for our increasing. So we're going to say we could write from 1 is less than or equal to x is less than or equal to 2, or in our interval notation, 1 to 2. Decreasing, on the other hand, is when the function is sloping negatively. So a negative slope would be going down that way. That's in our first chunk. Again, we're just going to use that first chunk of the piecewise. We would say from -3, including -3, all the way up to -2, or in our interval notation, we would just make sure to use that parenthesis at the end of the 2. A couple last hints when graphing piecewise functions. You can always check in Desmos. Remember, there are ways to restrict your domain. You can always Google that or ask your teacher, or maybe you remember. You can always restrict them in Desmos to check your answers. We also ask that anytime you are asked to actually graph a piecewise function, that you're very, very careful. Okay, so just a quick example with this. Obviously, I'm creating the graph here on my own, but let's say you were given this piecewise function to graph, 2x plus 3. Sometimes I graph the entire function without worrying about the domain because it feels easier. If I start at 3 and I want to slope 2, so I'll rise 2, run 1, rise 2, run 1. I could go also down 2 and back 1. Now, I could extend that line, but I'm going to go ahead and check the domain. I do know -1 is my starting value, so when x is -1, I actually have a dot here. I need to make one little edit because it does appear that I don't want it to be equal to that spot. I actually want it to be an open circle. So I'll go back with my orange and make it open because that -1 does not have an equal to. And then it wants to go all the way to when x is 2. So I would say when x is 2, 1, 2, I'm stopping up there. I'll connect this piecewise function, just that line from -1 to +2. And again, my grids aren't perfect, but just making sure you're a careful grapher and you start and stop as the domain tells you to. Finally, my second one is that boring y equals 5. So I like graphing this one. It's pretty easy. Now I could just draw a straight line all the way across there, but I do know my domain is from 2 to 4. When I go to 2, I want it to be 5. We got to be careful though here. It does not want it to be equal to. And we'll put an open circle there for that reason. Now it can be 5 all the rest of the time, all the way to when x is 4. So kind of a short little ditty there. Okay. One thing I can use this to talk about, guys, make sure that if you ever have an x value, let's say 2 here, where it equals 2 on this one, but it doesn't equal 2 on this one, you cannot have a piecewise function where at an x value of 2, they are different values. So again, the second blue one had a 5 and this top one had a 7. It would not be a function if they both were filled. So it's really important that whether you're writing the equation or graphing, you never have 2 solid dots stacked on top of each other. It's okay if they're the same dot, if that would fill this circle, but they cannot be stacked vertically on top of each other.